Okay, good morning, everybody. My name is Allan Bracker. I'm from the Naval Research Laboratory. I'd like to give you some insight into our little corner of a technology transformation that you're all likely to experience in the coming years and decades. And that transformation is going to come about from the explicit use of quantum mechanical effects in new technologies. So quantum physics is one of the great scientific breakthroughs of the 20th century, and it's really given us a much deeper understanding of the physical world. It's given us an accurate understanding of subatomic particles, electrons, quarks, and the Higgs boson. We can understand and really derive the periodic table of the elements and much of the chemistry of those elements, and everyday phenomena such as the color of the sky, the power of the sun, the hardness of diamonds, and even the nature of empty space. For technologies, quantum physics has already been a game changer, and often in ways that we're not fully aware of. It's given us the transistor, and that way the modern computer, lasers, MRI machines, atomic clocks, and other things that really wouldn't have been possible without a deeper understanding of the physical world that we've gotten through quantum theory. But in the last 25 years or so, a new technology revolution is building that's looking to take advantage of quantum measurement and quantum wave phenomena, such as superposition and entanglement. And these phenomena have the potential to create entirely new technology concepts and also radical improvements in the performance of technologies such as computing, communication, and sensing. And in these application areas in particular, they could have a huge impact on the ability of our military to gather and transmit and analyze information in a battle space that really includes the entire globe and beyond into space. So probably the best known example that you might be familiar with of a quantum technology is quantum computing. And a quantum computing algorithm takes advantage of the wave-like nature of matter to constructively interfere a quantum system so that we can select out a correct answer from a vast number of possible wrong answers. And although we don't have a large functioning quantum computer yet, we do have quantum algorithms for key applications such as data searching, simulation, and code breaking. And one impressive example is a quantum factoring algorithm, which can factor in a matter of hours a very large number that would take a conventional computer millions of years to factor. So probably nobody's too surprised that objects like atoms or electrons or protons show strong quantum effects, because these are sort of the prototypical quantum objects. But larger objects can also exhibit the wave-like nature of matter, from a quantum corral consisting of atoms positioned on a crystal surface to a very cold cloud of atoms known as a Bose-Einstein condensate. And at NRL, we're working with materials called quantum dots, and these are small particles, semiconductor crystal particles made up of thousands of atoms. And the ones that we work with are known as epitaxial quantum dots. And this means that they form a continuous crystal lattice with the substrate that they're grown on. So these are essentially solid crystal droplets of, in our case, indium arsenide semiconductor grown on a flat gallium arsenide substrate. And a typical quantum dot is 10 or 15 nanometers in diameter and several nanometers in height. And we can take advantage of the well-established tools of the semiconductor industry to fabricate electronic and optical devices. So for example, if we grow quantum dots inside a transistor or a diode structure and then wire it up in the right way, we can make a device that allows us to inject individual electrons one by one into a quantum dot. So because of their small size, quantum dots are often known as artificial atoms. When you confine an electron in such a small space, it can no longer move in just any way. Its motion becomes quantized. It takes on discrete values. And so we form an orbital-like energy level structure, analogous to the sp and d orbitals that you're familiar with in the hydrogen atom. We get a discrete optical spectrum so that light can only be emitted or absorbed at very specific wavelengths. And an electron in a quantum dot has a spin property. This can take on two values, which we usually call spin up and spin down. This two-level property is an example of a quantum bit, or qubit. But unlike a digital bit in a conventional computer, a qubit can exist in a quantum superposition state, which is it's a quantum combination of both things at once. And for an electron spin, we think of this as an arrow that's precessing at some intermediate angle between spin up and spin down. So at NRL, we've been working with quantum dot materials really since the late 1990s, starting with optical measurements on individual quantum dots and progressing to optical control and actually quantum logic on individual spin qubits, to more complex structures such as quantum dot molecules and quantum dots that have been incorporated into optical device structures, photonic waveguides and cavities based on a photonic crystal architecture. So what I want to do is just show you a couple of examples of problems that we've been working on in the last couple of years. So a quantum bit is obviously important for a quantum computer, but it's a little bit more general than that. We're actually trying to develop an electron spin in a quantum dot as a sensitive sensor of motion. So for example, this could be used as a sensitive accelerometer that could potentially detect heavy shielding material that somebody might try to use to conceal a dirty bomb. Or it could detect the presence of underground tunnels in a battlefield environment or some buried massive object. And so our idea is to use a very small cantilever containing a quantum dot and to look at the effect of a distortion or deflection of that cantilever on the spin superposition, an electron spin superposition in a quantum dot. And so we focus a laser onto the cantilever. This prepares and measures the quantum superposition. You can see in this graph on the bottom right an oscillation corresponding to that spin precession. And when the cantilever deflects or moves, we expect to see the change in the frequency that can be detected as a phase shift in that oscillation. So another problem we're working on is to develop quantum dots as a source of individual photons, single photons, which are important for quantum communication. So quantum communication provides a means for doing ultra-secure encryption. It's based on a fundamental physical fact that it's impossible to copy a quantum wave function. So if a sender and receiver have a message or sending a message that's being intercepted by an eavesdropper, they will always know that that eavesdropper is tapping in. So quantum dots are actually an excellent source of single photons, although it's most common these days to use a laser. Obviously a laser creates a lot of photons, and if we attenuate the laser with a filter, we can get down to the level of individual photons. The problem is that they come at random times, and the communication would be more efficient if they came at regular times. And so with a quantum dot, we can actually make a triggered quantum or a single photon machine gun. And so we've been working on a special type of photon machine gun using quantum dots, where we use laser pulses to trigger the appearance of individual photons from the quantum dot at a slightly different wavelength. What's powerful about this is that we can map the properties of the laser pulses onto the properties of the individual photons. So if we change the color or the wavelength of the laser, we get a corresponding change in the wavelength of the single photons. And if we change the duration of the laser pulses, we get a corresponding change in the duration of the single photons. And so this flexibility allows us to adapt it for different applications or different device architectures and device concepts. So finally, I'd like to describe something, a very new thing that we've just begun to work on. It would be useful if this stream of single photons, if individual photons were actually entangled with each other. And so entanglement is one of those quantum mechanical concepts. It's a little bit hard to wrap your head around, but basically if two or more objects are entangled, then their wave functions cannot be separated. So even if the objects are physically separated and no longer interacting with each other, it's as if there remains a causal connection between them. And so we and others have shown that it's possible to entangle an electron spin in a quantum dot with a photon that's been emitted by that quantum dot. But if you can do this once, then if you're careful, then you can do it multiple times. And if each photon is entangled with that spin, then the photons will be entangled with each other. And if we want, at a later time, we can actually disentangle the electron spin. And so why would we want a chain of entangled photons? Well, one way of doing quantum computing is to use photons as qubits. And it's very attractive, the possibility of being able to do quantum computing with photons in a very compact silicon integrated photonic circuit device architecture. So this quest for quantum technologies is really a worldwide effort, and it's been building up steam in the last several years, especially. Big companies like Google and Microsoft and IBM have gotten involved, many universities and national labs, and the US defense and intelligence agencies are actively supporting this effort. Our work was funded by the Office of Naval Research, by DITRA and DARPA, and by the OSD Quantum Sciences and Engineering program. And so this is a challenging field. A lot of work remains to be done, and a lot of basic research remains to be done. But it's exciting now that as we're actually approaching the 100th anniversary of the birth of quantum theory in the 1920s, that we're also now, at this point, entering a new era of quantum technologies. Thank you.